Hello Year 12. So we're starting a new topic on a new module. It's a new start. This is the first video and it's about enthalpy, and things are really going to heat up in this video if you'll excuse a terrible pun. These are specification points we're going to cover. Apart from the last one, ignore the last one. The rest are what we're going to cover today. It looks like quite a lot, but actually they're pretty easy. A lot of it's GCSE revision. Some of it's going to sound really complicated. Just have a little time, let it settle in. Hopefully by the lesson you'll be feeling good on it. And if not, by the end of the lesson you definitely will. So, enthalpy. Enthalpy is quite a strange concept. Enthalpy is kind of the chemical potential energy. It's the grown-up way of thinking about chemical potential energy. It's the amount of energy within all the bonds and all of the rotations, all of the stuff within a molecule that we can get out by doing reactions. Unfortunately, we can't actually measure enthalpy. There's no way that I could stick a probe into some molecules and have a look at what the enthalpy of it is. However, I can measure, and you can, we can, as scientists, measure the enthalpy changes during a reaction. So we give the symbol H for enthalpy and the symbol delta H for change in enthalpy, because delta always means change. This is because of the law of conservation of energy, which I've just written out there. I'm going to read it out for you. You can read. So what would happen is that you would, if there has been a reaction that is either released or taken in heat, we'll be able to see it in the change in temperature of the surroundings, because that heat, that energy that we release, or the energy that we change during a reaction, has to go somewhere. Let me show you what I mean. In an exothermic reaction, the reactants have a higher enthalpy than the products. So we start off with more enthalpy than we end up with in our system, in our chemicals. So that enthalpy, that heat, has to go somewhere, and where it goes is to the surroundings. So what you'll notice during an exothermic reaction is the temperature increases. Examples of this are combustion and neutralization, and the tricky thing to remember is that despite the fact the temperature is increasing, the enthalpy of the reactants, or the enthalpy of the chemicals, of the molecules, has decreased. The enthalpy of our system has decreased, but the energy of our surroundings have increased, so we measure an increase in temperature. Examples of exothermic reactions, as I say, are combustion. That's a classic one. Always use that one. If you imagine burning some methane. The products are water and carbon dioxide, and they are of lower enthalpy than the reactants, so we release the heat to the surroundings. Endothermic reactions, the converse is true, delta H is positive. So for example, here we've got the thermal decomposition of calcium carbonate. You have to put in 178 kilojoules per mole. Don't worry what that means, we'll talk about it later. But we have to put in some energy in order to raise the state of calcium carbonate to these calcium oxide and carbon dioxide, which are of higher enthalpy than calcium carbonate. That energy is taken in from the surroundings, so the temperature of the surroundings would decrease. Obviously, this is a thermal decomposition. You wouldn't be able to measure that decrease very well because you're putting fire underneath it, but you could do if you were very good. Now, the grown-up way of showing an enthalpy change is using an enthalpy profile diagram. The x-axis is the progress of the reaction, as we go from reactants to products. It's quite a sort of stylized model thing. And the y-axis is the enthalpy, or H, as we put it here. We have the reactants on one side, the left-hand side, and the products on the right-hand side, as you can see. And we have two labels here. There's a little hump in the graph. That hump represents the activation energy. In order to get from our reactants to our products, we have to jump over the activation energy barrier, because the activation energy is the minimum energy required for two particles colliding to react. Delta H is negative in this case. It's an exothermic reaction, so our products have a lower enthalpy than our reactants. Notice the delta H is the difference between these two levels. We don't include this, we ignore this for the delta H. In an endothermic reaction, we still, even though we're going up levels anyway, we still have an activation energy. You have to jump over this little barrier here to get to our products. And the delta H is this bit here between these two. Okay. So the last thing I need to do is run through some definitions with you. Now, there's quite a lot of definitions of things, of different quantities in this unit. First we need to learn is the standard conditions. Every time we talk about the enthalpy of a reaction, the enthalpy change of a reaction or something like that, we talk about the conditions of it. And if it's got that little weird, I always think it looks like the London Underground symbol at the top right of the H, as a superscript to the H, then that means it's under standard conditions. So standard conditions are 298 Kelvin and 101 kilopascals. 298 Kelvin is the same as 25 degrees Celsius because, as you should know, to get from Celsius to Kelvin, you add 273, sorry. Standard enthalpy of reaction. So the enthalpy, we have a few defined quantities, a few defined enthalpies. So for example, the standard enthalpy of a reaction, if we see that symbol, delta H, standard, the enthalpy change when the number of moles of the substances in the equation as written react under standard conditions. So for example, if I took 1 mole of sulfuric acid, I reacted it with 2 moles of sodium hydroxide, 298 Kelvin and 101 kilopascals, then I would have the standard. I would be able to measure the standard enthalpy change of reaction by looking at the change in temperature and doing some maths on it. Another way of saying the number of moles as written of the substances as written in the equation is by saying in stoichiometric quantities. So the enthalpy change when reactants in stoichiometric quantities for a reaction react under standard conditions of 298 Kelvin and 101 kilopascals. Next one we need to know is the standard enthalpy of formation, and that's the enthalpy change when 1 mole of substance is formed completely from constituent elements in their standard states and standard conditions. Now notice the thing that we're looking at the formation of is the product of the reaction. So if I was looking at the standard delta H standard of formation for water, then water is the product, and I need to make 1 mole of water. To make 1 mole of water, I need 1 mole of hydrogen gas in its standard state at 298 Kelvin, which is H2 molecules, and half a mole of O2 molecules. Do you see what I mean there? Because O2 in its standard state at 298 Kelvin is O2 gas. It's okay to use half a molecule here because that it has to be to form 1 mole of the product. So we're allowed to use halves in our equations now to balance them. We do need to make sure they're balanced though. Final definition is the standard enthalpy of combustion. It's kind of the flip of standard enthalpy of formation. So if we look at the standard enthalpy of combustion of methane, it's the enthalpy change when 1 mole of substance is burned completely in excess oxygen under standard conditions of 298 Kelvin and 101 kilopascals. That's the starting conditions, obviously. So if I burn 1 mole of methane in 2 moles of oxygen, so I've had twice as many moles of oxygen as I had methane, and made 2 moles of water and 1 mole of carbon dioxide, I would be able to measure the standard enthalpy of combustion of methane. Right, have a little look through the definitions, try and get comfortable with them. You need to remember them. I will be testing you on the definitions in the lesson, and I will be testing you on the definitions every lesson because you need to know them. Hope this has been helpful. Thanks very much and have a good evening.